So this video is going to cover the different states of matter, solid, liquid, and gas, and how we convert back and forth between them, how we determine the energy associated with them at various conditions, and so forth. So we're going to take a look at heating and cooling curves, and we're going to take a look at phase diagrams. So first off, just as a refresher, you've got three phases of matter. Gases we've just got done looking at, so those are pretty familiar to us. Gases were a good starting place because we assume that the interactions between these particles are negligible. So their behaviors are, for the most part, independent of how they interact with each other. Liquids and solids, however, not quite the same story. Liquids and solids are particles that are much closer together. They do interact with each other, so we can't ignore those attractive forces. But they actually have very similar behaviors, similar density, similar compressibility, so on and so forth. So we lob liquids and gases into the same category in terms of behaviors. All right, so once again, just a nice review. Gases, because there's no interactions between them, they can spread out and take up the shape and volume of whatever container you put them in. We can easily compress them, they flow, diffusion within a gas occurs rapidly. Then you compare it to liquids, okay, so here we've got the gas, which is very disorganized, a lot of empty space. Liquids, molecules are much closer together. In order to get from a gas to a liquid, we have to cool it or increase the pressure to compress those molecules closer together so that interactions do start to occur. So in liquids, you still have a whole lot of disorder. You have some interactions, but not a lot. So the liquids are able to take on the shape of their container. But they do have a definite volume. They don't expand to fill the container. They have a definite volume. But they're free to move around and move past each other. So they have a good, they flow readily. Diffusion within a liquid happens more slowly because obviously the molecules are much closer together. And a liquid is pretty incompressible. The molecules are pretty much as close together as they can be. You continue to take heat away and you go from the liquid phase to the solid phase. Here you can see we have a very organized structure, a lot of IMFAs, a lot of interactions, attractions holding those molecules together. So they maintain their shape, they maintain their volume, they don't flow, nothing diffuses in them very easily. And so these guys are pretty rigid. All of that, hopefully, you know. Here's an important idea, though, over here on the left. The state of the substance, so whether it's a gas, a liquid, or a solid, depends upon the balance of two things. The amount of kinetic energy, so temperature, and the IMFAs, the attractions or the interactions between molecules. So essentially, we're looking at in kind of the idea of pressure. So just as a refresher in terms of changes of state, if you go from a liquid to a solid, it is freezing. If you do the opposite, if you add energy, so here we're taking energy away to get from a liquid to a solid. When we melt, we add energy, so we go from a solid to a liquid. Liquid to gas, if you add energy, you vaporize it. If you cool it, you condense the gas to a liquid. And then the two terms that are least familiar to you probably, sublimation is when you go from a solid to a gas, and deposition is gas to a liquid. So the red ones, we're adding energy to get to a more disorganized state. We're breaking up attractions in order to get the material from a more organized state to a more disorganized state. Versus the green ones where we're removing energy in order to create a more organized state, increase the number of attractions between the molecules. So most attractions in the solid phase, least or actually no attractions in the gas phase. All right, so let's continue on with this idea of phase changes. So as we go from a solid to a liquid to a gas, just keep in mind that we're not changing the substance. There's not a chemical reaction going on here. This is strictly a physical change. You still have whatever the molecule is that you started with. Water, for example, stays H2O, whether it's an ice or liquid water or steam. The attractions between the molecules do change. So many attractions in the solid form, but no attractions in the gaseous form, or essentially no attractions. And so in order to get from solid to liquid to gas, we have to overcome the attractive forces to get up there. So we have to break some attractive forces to go from solid to liquid, and then we have to break the rest of them. All of the attractive forces have to be broken in order to get to the gaseous state. And so the amount of energy that's associated with those changes are referred to as, well, a couple different things. The heat of fusion, hopefully you remember this. Heat of fusion, converting from a solid to a liquid. Heat of vaporization, converting from a liquid to a gas. Or heat of sublimation, where you go directly from solid to gas. So, for example, solid carbon dioxide sublimes. It becomes a gas immediately. That's what dry ice is. Dry ice, that smoke that you see, that vapor that you see, is gaseous carbon dioxide. You never see dry ice melt, it just sublimes. And so the energy associated with that, this is the heat constant, the energy associated with that change depends upon the quantity of material that you have. So Q is an extensive property, delta H is an intensive property. So the extensive property depends upon quantity. So you've got mass or moles times delta H. So that brings us to the idea of the heating curves that we saw in first year. You've got 5 different sections in this heating and cooling curve, as marked as AB, BC, CD, so on and so forth. The diagonals are where we are changing the temperature of the material within its own state. And then the plateaus are where we are doing state changes. So let's just kind of review what's going on there. So at the plateaus, we're doing phase changes. The energy that is used in order to achieve this state change is referred to as the delta H values that we saw in the past. So Q equals N or M, so the number of moles, the mass, times delta H. So what are we doing here? We are breaking those attractions in order to get from one state to the other. Notice that energy is not increasing or decreasing at these plateaus. So we're not changing kinetic energy, we're changing potential energy. We're rearranging the attractions. We're breaking attractions apart in order to go up this curve. So again, temperature change is constant because energy is going into breaking those intermolecular forces, those attractive forces. At the diagonals, now you do see a temp change because we are changing the kinetic energy of the material. This is where specific heat comes in. We've talked about specific heat before. So how much energy does it take to change 1 gram of material 1 degree Celsius? That amount of energy is what's controlling the steepness of the line. And so remember that the energy associated with that is Q equals MC delta T. Because there's a temp change, we have to consider that in addition to the quantity of material and the heat constant. So in both cases, we've got the quantity of material and we've got the heat constant. But in addition, when we're doing simply heating or cooling something, we've got that temperature change associated, so that's got to go in there as well. So units, delta H is typically kilojoules per gram or kilojoules per mole. Specific heat is joules per gram per degree Celsius. So temperature is changing because the kinetic energy of the molecules is increasing. So the molecules are, if you remember, vibrating, rotating, and so forth more as you increase the temperature. Those vibrations eventually come to a head where we start breaking some of the attractive forces. Once we've got it into that liquid state, once again, we're going to cause the molecules to vibrate more and more and more and more and more and rotate and twist and all that kind of stuff until we've got so much rotation that we start breaking the rest of the attractions between the molecules. And at this point, we've got all the attractions broken, and so the molecules not only vibrate and rotate, but they can move from one location to another, which is what they couldn't do in these other two phases. So if you remember, we have vibrational energy, we have vibrational and rotational energy, and then we have vibrational, rotational, and translational energy. Couple other terms that we didn't see last year. Critical temperature is the highest temperature that you can get a material in its liquid phase. Above the critical temperature, the molecules possess so much kinetic energy that they've got so much movement with them that it doesn't matter how much you try and compress them together, you can't get attractions to form, and so you can never get it to become a liquid again. So at this point, at the above the critical temperature, you have a gas, and you cannot pressurize it enough in order to make it a liquid. You have to lower its temperature in order to get it to become a liquid. Obviously, then critical pressure is the pressure right at that critical temperature. So right at the point where you can actually liquefy the material, so the molecules are moving so much at this critical pressure that it's the pressure that's required to get those molecules to actually stick together. So if the critical temperature is very high, the critical pressure is also going to be very high. All right, so we got a couple examples of heating and cooling curves, but I'm running out of time, so I think we're going to go on to a second video in order to show us that.